Hello, everyone. Can you all hear me? Okay. So usually Tony gives our wonderful presentations on what we're doing in the chemistry space at NCCT. But since he's chairing today, you're going to have to deal with me. And my presentations are a bit more mundane, more focused on the data rather than the interfaces that we build. And I just want to, make sure that you don't blame them for what is actually in this presentation, because neither of them actually got to see it. So NCCT's purpose in the EPA is to provide data for chemicals. It's to gather up a whole bunch of information and make that available for people. And so we have a lot of ways to do that. We have a lot of efforts around producing data from models, from algorithms, using software. We have in vitro screening assays that we are running in ToxCast, which generate a lot of data. And then we want to make that data available to people and for other people to use it. And this has always been difficult for us because it's hard to make other people want to use your data, especially when you put it out in 20 different CSV files, like we have with ToxCast. But at least we try and put it out. So ToxCast, we run the assays, we generate the data, and then we make it available for download. Why do we do this? We do this because, as Lyle said, the standard environmental chemistry reason. There's a lot of chemicals in the environment. We know very little about many of these chemicals. And so we need to try and gather the information on these chemicals, both in the public domain and for the portions of the chemical space that we're interested in that are CBI, so that internally we can provide good information to our regulators. So, quick step directly into chemistry, because chemistry is where my heart and soul lives. We look at our chemical space in sort of 4 layers. We have test sample data. That's what we actually run in wells. We have generic substances where we try and aggregate that data up to a chemical substance. And that's typically what people think of as a chemical. Then you have a structure. And structure may not exist for a particular generic substance. There are many substances where we cannot properly identify a structure that accurately represents that substance. Either they're mixtures, they're partially defined chemicals where it's some sort of mixture of alcohol components, or you know that the molecular weight is in this range here, but you don't know exactly where the substituent is. And we'll talk more about things where you have a generic substance but not a structure later when I talk about UCBBs. And then we have structural abstraction, where we try and take those structures, abstract some sort of information about those structures, and coalesce data around that abstraction, either through the generation of SARS or QSARS, or doing read-across methodologies, which Grace will talk about tomorrow, I believe. So, our chemical database is DSSTox, and it has been DSSTox since 2004, when Anne originally created the project and put out the first publications related to it. So the purpose of DSSTox was to collect interesting sets of data and accurately map chemical structures to those sets of data. And in doing so, she focused primarily on high-impact sets of data that were available in the public domain, and they were indexed by path numbers or names and never had structural information available for them. So, things like the carcinogen potency database, chemicals that were known to be in drinking water and disinfection for drinking water, the fathead minnow-toxicity database. And then DSSTox, when ToxCast screening started, got involved in all the registration of the chemicals that are actually in ToxCast. And so we managed all that chemical registration, and all of this was done fully manually. So Anne, with a team of 2 curators, would go through these identifiers, do searches on the internet, collect up the information, that real hard work that Thomas is trying to get us to have to technological solutions for, they did it all manually. And by 2014, they got to 20K substances where they manually curated the information, the mappings between classes, names, and structures, providing us with a really clean data set of identifiers mapped to structures. So when I came in 2014, I looked at the database and I was like, oh, this is really nice data. It's really accurate. People have been cleaning it. They really are making sure that the mappings between identifiers and structures are right. Looks great. It had the capability of doing structure sub-searching within specific subsets of data, which is really valuable if you're trying to find analogs that have particular data associated with them. And it maintained a one-to-one-to-one relationship between names, CAS-RNs, and structures. This is really helpful when you're trying to clean your data because a lot of data comes in, you're trying to figure out what is actually meant by the identifiers, and if you don't have a clean listing of what an identifier means in terms of structure, you're really going to be having a lot of problem trying to figure out what that person was talking about when they ran their essay. And so it really had a three-table data model, which was list records, which I refer to as source substances, the generic substances, which are where we collapse data to based on name and identifier information, and then the structures themselves. But it also had many weaknesses. So it was all in spreadsheets, and so we definitely had the too many spreadsheet problem. And we could avoid the Excel problems that you were discussing with CAS numbers. And we actually have fixes for those if you need any help. It was also too small. 28,000 structures is simply not enough for the number of chemicals that we're interested in the public domain. And the other databases that were out there for chemical information had millions by this time. And so there was certainly a huge gap between where we were at in terms of the chemical information we stored and where other places were at in terms of the chemical information they stored. And the process was way too manual. So everything was done by hand, an individual going through and checking stuff. And every check had to be done by hand. There was no programmatic assistance in the curation effort at all. So first thing I did when I came in was I immediately took their spreadsheets and dumped them into a database. And so this is the data model that we have. Generally, it's sort of a simplification of the data model where you have source substances, which are referenced by DTX RIDs. And these source substances link out to the actual data that we pull in. So this is how we integrate our data. Everything comes in, it's registered with a DTX RID for the substance information that it contains, the CAS number, the name. If they have a structure associated in their database with it, it all goes right into here. And then we manually map this information to the actual core information we have in DSSTox, where we have accurately mapped names to structures and CAS number name relationships for the past 20 or past 15 years. So this is a primary area of curation, but this is also a primary area of curation. So this is what I refer to as DSSTox core. And we have one curator who's just going through our databases, making sure that these identifiers in our between generic substances and structures are correct. And then we have other people who are going through and saying, all right, we have this particular list that we're interested in that has associated data. Let's make sure that when we take in their information, we properly map it and coalesce it to the correct substance. So that takes care of the too many spreadsheets problem, but it doesn't take care of the too small or too manual effort. So when I came in, one of the first things I did was I went out to the public databases and I started pulling all the chemical data that was in the public domain. And we chose to start with 3 primary databases that we saw that had generally pretty good data, well, at least the first 2. And that was EPASRS, which is the Substance Registry System at EPA, which is a public listing of all the identifiers that are important in regulatory domain according to the EPA. And then ChemID Plus, which has been generating and storing public cheminformatics data for the government for a long time. And then we also pulled in PubChem. And so I'm going to give you an example of what happened when I tried to coalesce that data and put it into my database, DSSTox, which had been highly curated up to this point. So there were a total of 77,000 chemicals in EPASRS. They had associated with them 2 systematic names and a SMILE string, all of which I converted to structure so that I could do comparisons on structure. And then they also had a CASRN. CASRN is generally considered a unique identifier of a chemical substance. So when I started doing checks and assumed that a CASRN should be a unique substance, what I found was there were lots of cases where all the identifiers that they had associated agreed to and were describing the same substance. But then there were also a lot of cases over here where there was disagreement in the identifiers in the database itself. So the name that they had could not possibly mean the structure that they were providing in the SMILE string. So these did not get loaded into the database. Then I took these ones that there was agreement or there was only one thing that would actually convert into an HET, and I checked it against the other sources we had, ChemID and PubChem. And you can see here that I'll just sum up these numbers here. The internal disagreement inside SRS itself was roughly 12% of the chemicals they had in their database had internal disagreements about what that chemical was. When you go back and look at that CAS number in other databases, 24% of the ones that did not have internal disagreement in SRS, when you went to ChemID Plus or PubChem, they would give you a different structure for that CAS number. And then even the ones that passed the checks both in SRS and in ChemID and PubChem, when we checked them against the replicates that we already had in DSSTox for that database, you still had 10% disagreement in what the actual structure was. So this is the level of uncertainty that you have around structures and identifier mappings in the public domain. So I went through, I loaded the data in. DSSTox now has roughly 750,000 chemicals in it. However, you have a much smaller realm where the data was consistent. You have 600,000 of the records where the data is simply PubChem has this chemical, but we don't know what it is. And so that's why it's so important to always look at these QC levels when you're looking at DSSTox chemical structures. We are very confident that we have properly mapped identifiers in this space. We're fairly confident that with programmatic curation, we have pretty good identifier mappings in this space. This space is the space where there were untrusted things which have not been loaded into the database yet, although those conflicted structures at some point we will load in and mark them as having conflicts. And then we have things where there's no verification. There's one source, but we have no idea what that data actually means. And so then I also created a simple interface for registering new chemicals into DSSTox. This interface will check things to verify that we don't create duplications in our database and that our data remains clean going forward as we do our manual curations. So what does this provide? Well, this data underlies the ComTox dashboard that we make available to the public so that people can search our data and be able to find chemicals that we are interested in. If I can get it to show up in the right spot. So, simple search for something like atrazine. Yeah, I know. I'm having problems with having multiple keyboards here. So you can see that we have a autofill in here that allows people to see things as they type substances that we may have that are associated with the thing that they are typing in. In this case, if we search for atrazine, You come to our generic chemical page. This is what we put up for all chemicals when you do a search. And here you can see that we specified that this was found by an approved name. So this is a preferred name. There are many different types of identifiers that we have in our database, different levels of synonyms, dependent on the level of trust that we have in those synonyms. And so if you go down and look at our synonyms table, you can see that we have very few things that we actually think are really, really valid names, and a curator has taken a look at them and marked them as valid. There's a huge number of names where there's less certainty about whether that identifier is the best mapping for that particular substance. But we put them in here because otherwise you can't find anything if you only live by truly validated data. You'll also note that that during my analysis I made an assumption, and that assumption was that CAS numbers are indeed unique for a substance. And the truth of that is that they are not unique for a substance. A little secret about CAS numbers is there are many cases where you have an active CAS number, but then you also have deleted CAS numbers. These are CAS numbers that should not be used anymore in the public domain. They are numbers which have been officially stamped, do not use by the registry service, and they exist attached to data. So all of these things have to be documented in your store of identifiers that exist for a particular substance. So, I actually skipped a step here. I am sorry. So I was going to show you that we actually have a lot of data in that dashboard. That data is data that we have collected, and we've done exactly what Thomas has been talking about, where we pull data from different places, and then we map it into our data structure so that we can use it. As we are mapping that data into our data structure, we are using that 3-layer model in order to properly identify what we think the real substance was that was associated with the data. And the way we do that is through a list curation interface. So this is a list that we pulled in. It's the Allen Wood database. It's commonly referenced as one of the best pesticide databases that are available on the web. And if you take a look at it, there are cases in the data file that we had from 2 years ago where there were duplicates in that database, where they had a CAS-RN that was on more than one substance, where they had structures that were duplicated across substances in their database. And then they had 2 cases where their CAS-RN was not even a valid CAS-RN. It didn't meet checksum requirements, or it did not have proper CAS format. Then we take those identifiers, and we have programmatic mapping that takes that list of identifiers, maps it to the list of identifiers that we have in our core structural or our core generic substance table in DSSTox, and evaluates how good those mappings are. And so you get many different levels of mapping. And so you can see that you can have cases where the structure and the preferred name and the CAS-RN all matched. That's a really good record. That's something that we can be very confident that the mapping between the data in Allen Wood and the data that we have is intending to document the same chemical. But as you go down here, you find other records. This one had deleted CAS associated with it. This one mapped on unique synonym rather than on preferred name. And so it's a little less certain whether or not that mapping between the substance and data actually is the same as the substance that we are trying to document in our database. Now, why is this important? Why do we curate? Well, we have so far loaded 110 different lists into DSSTox from different sources. In that list mapping, we can have a fraction of the set which is unmapped. We don't have anything in DSSTox which maps to the identifiers that they're using. Or you can have things where they had a CAS and a name, and in our database, that CAS and that name mean different things. And so here you see the fraction of different sets that are unmapped. These that are particularly high are when we go out and grab really large databases, like the mesh database of chemicals. And we are missing a huge amount of chemical space in this database that we have right now. But more worrisome is this axis where you have the conflicted identifiers. Because what this means is, on average, if you look at where these plots distribute, about 5% of the data that comes in the chemical data files that we try and load, you don't know what chemical they're actually talking about in that data file. There is a conflict that makes it impossible, without going back to the original source and talking to the people who created the data, what chemical did you actually test? What chemical is this supposed to be associated with? We're also doing a whole bunch of other things that go beyond just list mapping. We are trying to document the associations and families of chemicals. So for something like PCBs, we have documented all the associated all the associations to the family members. And so you can go here and just search PCBs. It'll pull up that it has a CAS number. It's a substance. What it really is it's a family. And so under record information, you can see that we have done our due diligence. It's level 1. It's been expert curated. The quality control notes describe for you what it actually is. It's a biphenyl. And we don't know how many chlorines are on this thing. But most powerful is the ability to export for these types of families, SDFs, Excels, TSVs, that give you the structural information. And we're really hoping that in the future, we'll be able to take this sort of relationship diagram based on these structures, do predictions of all the different components underlying a particular family, and give you distributions of what we expect for particular parameters based on QSAR model. If I can get my presentation to come back up. We also are trying to go to the next step. So right now, all of these relationships where we map substances to different family members, for example, in the case of xylene, we have the CAS numbers for O, N, and P xylene. Here we have simply an example of a C6 to C12 ethoxylated chemical. We are hoping to move these things to the point where we're drawing Marcuse structures for them, trying to accurately document what they are so that these are programmatically accessible and we can enumerate these things instead of having people manually generate all the associated chemicals that exist underneath a particular thing. So that's where we're at right now. There's still a ton of work that we need to do around proper mapping of substances and properly mapping identifiers in the public domain. But what I want people to take away from this is the data models that are traditionally used in the databases are insufficient. They don't allow the curation of this step and the curation of this information. You really need 3 layers in order to properly map these types of data, whether they come in from sample data or from lists of data that people have aggregated out in the public domain. Always be careful when you are getting public chemical data and you're trying to map things to structure. There are tons of cases where you see VBs, chemicals with unknown composition, are directly mapped to chemical structure. And if you use that chemical structure, you're making an assumption that you think that structure is actually representative of the entire mixture that you are trying to regulate. And finally, please take and use our data. So, there is a capability here to do batch searching. And in this batch search, you can put in a name, you can put in a CASRN, you can put in an NGT, and you can map these things into our database and pull out the DTX SIDs. These are invariant identifiers, which will always mean a particular substance that we thought they meant when we created the record. A particular chemical for a DTX, a particular structure for a DTX CID, a particular source input set for a DTX RID. You can also export a huge amount of the other data that we have mapped. So if you go down to the download chemical data, there's a lot of different things that we have available in here, many of which are intended to support our internal efforts, but our goal is to continue adding data into this interface so that people can export it and use it in a pretty simple way. And finally, we have a downloads page, and this downloads page provides data in simple file formats that are generally used for chemical data right now, which Excel, SDF files, things with INCHI keys in them, that sort of information that we make available for people to take away and use however they see fit. So, I have an acknowledgement slide if I can get to it. And so that's the wonderful place that I work. I'm happy to be there. And these are all the people that helped with development of the dashboard up to this point. And we have new people coming on to help that need to be added to this slide. So thank you guys for your time. And if you have any questions.